Hi, this is a video about sections 5.2 and 5.3 for tomorrow. That's about the graphs of polynomials. And so a polynomial is just made up of power functions. And power functions are functions that are just like a constant times the variable to a power. And so it could be area is pi times r squared, or volume is 4/3 pi times r cubed. But they're in general, they're functions that are k times x to some power. And what we're going to be looking at is when the powers are exponents, or are integers, when the powers are integers. And if they're even powers, then they're similar to the parabola, like x squared. And so x to the x squared, x to the fourth, x to the sixth are similar graphs like this. And the main difference is they get kind of flatter at the bottom when you have a higher power, if you graph those. And then they get higher, faster, steeper. But when you square or take something to the fourth power, everything's even on, or positive on both sides. So it goes positive up on both the left and right. An odd function, an odd power function is similar to x cubed, or even, they don't put it in the graph, but in the book, but even y equals 1 x to the 1 is similar. It starts off negative and ends up positive. And x cubed and x to the fifth are the same, but then they kind of flatten out for a second in the middle near the origin at 0, 0. And so what we're going to look at are polynomials, which are functions that are made up of adding together a bunch of terms that are, each one is a power function. And so it's going to be something like 3x to the fourth minus 5x cubed plus 2x plus 17, or something like that. It's going to be a bunch of terms, and two things are going to be important. One is the leading term, which is the term with the highest power, and the other is how to factor. And so polynomials don't always look like in that form. They could be things like this, where you have to multiply it out before it looks the right way. So that's a polynomial. Or they could be in a form like this one, where again, if you multiply it out, you get two power functions added together. So that's a polynomial. But things with square roots and cube roots, those aren't polynomials, so they won't follow the same rules that we're going to talk about in this section. So there's really, when you see a problem that has a polynomial in it, there's really two or three things that we're looking for about the polynomial. Like I said, if it's written in the standard form, we're going to talk about the leading term of it. And that's the term with the highest power of x. And that highest power will be the degree. And we'll talk about it being a cubic or a degree 4 or a degree 5 polynomial. And the leading coefficient is the constant of that term. And so what that allows you to do is something called the end behavior. And what that means is if you have a polynomial, if x is very big, then this leading term with the high power is much bigger than the other, and it kind of dominates the other terms. And so the end behavior, and I'll show an example in a second, is similar to just what that leading term graph looks like. And so that can get you started on what the graph overall looks like. Second, if you can factor it, which is sometimes not easy, sometimes we won't do, sometimes you need a trick to factor it, and sometimes you won't be able to. But if you can factor it into a factored form like this, where it's some number times x minus one root and x minus another and x minus another, those show you the x-intercepts, right? Or the roots of the polynomial. And that's where it crosses the x-axis, where it's equal to 0. And sometimes, if you factor it, you might have a power in here. And so that would be a root of multiplicity 2. It's kind of like you have a double root. Or if it's even to the third power, that would be a triple root. So if we talk about multiplicity, that's what that means when you factor it out, if it comes out with a squared term or a cubed term. And so when generally you have a polynomial, you're going to have the end behavior, which is what happens off to the right the graph, this one happens to go up as you go off to the right, and it happens to go down as you go off to the left. But it's possible that it would end up turning around and going down to the right. So the end behavior is either positive or negative on the right side, and either positive or negative on the left side. And we're going to figure out how to determine that. We're also going to figure out if it's factored, we can find the x-intercepts. And generally, not always true, but generally, if a polynomial is degree n, it's going to have n minus 1 local maxes or local mins, so peaks and valleys. And so a polynomial will be a kind of up and down roller coaster, and based on the degree, you can have some idea of what the shape should be. So let me give you an example. So here's a polynomial like this, and it's already factored. Okay, so we know the roots are when x squared is 0, or x minus 1 equals 0, or x plus 4 equals 0. So that's x equals 0, x equals 1, x equals negative 4. So if it's already factored, you can easily see what the graph looks like from that perspective. And so it's going to be, it's going to have a, let's change the color. It's going to have 1, 2, 3, 4, at negative 4, at 1, and at 0. And then the other thing that you can do, if it's in the general form where it's multiplied out, you can look at the leading term. So imagine we took that and multiplied it out. We would have minus 3x squared times x squared minus 4x plus 4x minus 1x is plus 3x minus 4. And so then we multiply that through minus 3x to the fourth minus 9x cubed plus 12x squared. The leading term is minus 3x to the fourth. And minus 3x to the fourth, x to the fourth is a graph that looks like that, right? Minus 3x to the fourth is going to look like that, upside down and flat. That's a terrible drawing, but pretend. The main thing is it starts off negative and it ends up negative. That's its end behavior. And then that allows you to kind of graph the function. And in a little bit, I'm going to show you on a Desmos activity how the multiplicity of the function can help you draw it. But you start off on the end behavior, and you go through the roots. And x equals minus 4 is a root. X minus 0 is a root, but it's a root of multiplicity 2. And I'll show you in the Desmos thing why this works. That means it's multiplicity 2. So it looks like a parabola-ish. It's not exactly a parabola, but it kind of does. It bounces back. And then it has to go through the last root. This is a root at x equal 1. So most of the roots, the graph crosses through the x-axis. But if it's a multiplicity 2, then it's going to behave like a parabola and just touch that root. So without doing much thought, if it's factored, we can know where the roots are. We can multiply it out and find the leading term. You don't even have to multiply it out to do that. If you look at this, the original polynomial, we've got the minus 3x squared, then another x and another x. If you imagine foiling this out, just take the first terms of each part. And that's going to be minus 3x squared xx is our minus 3x to the fourth. All the other terms end up being less significant when x is big, so on the far left and far right of the graph. So you can look at that polynomial and know it's got degree 4 and a negative leading coefficient, so it's got to look generally like this thing we have on the right without doing any calculations. Sometimes, though, you have to factor it, and so we're going to practice factoring a few times, and sometimes you see little tricks, and this is an example where all of the powers in this polynomial are even. So what you can do is you can factor it as if it were x squared and x squared. Those are going to get multiplied to give you the first term of x to the fourth. And then what goes in here and what goes in here, like we've done before, the last times the last has to give you minus 45. And the inside and the outside are going to have to give you minus 4x squared. So you can probably think about this and figure out that it's going to be minus 9 and plus 5 is a way to factor that out. And once you get started, then this one you can factor as x minus 3, x plus 3. And this one doesn't factor anymore. Can't factor. And that happens over the real numbers. If that were equal to 0, you'd have x is going to be the plus or minus square root of 5 times I, if you know complex numbers. So we're going to ignore that, and so we're going to say that that has no real roots. So you can get a graph of this by what we've just done. What's the end behavior of this graph? Well, it's, if you look back at the start, it's an x to the fourth graph. So it's going to look like that. But we just ignore the middle part, and we've got this part and this part. So what that means is on the ends, it's going to look like x to the fourth. In the middle, it'll bounce around a little bit. And so we can then graph the 1, 2, 3, negative 3, and 1, 2, 3, positive 3 are where it crosses the x-axis. And what we can do then is it starts at the positive and ends at the positive and goes through those 2 points. But that looks like a parabola, and that looks like it's degree 4 or degree 2. If it's degree 4, it probably has an extra little bump in it that we can't really do precisely, but we can have an idea and expect some extra little thing like that to happen. And that's because it has this extra term in there that doesn't actually make it have a root in it. And I'll show you, we can play around with that on Desmos, how those work. I wanted to show you how you can think about this with a Desmos app, how looking at a fourth degree polynomial. So what I've got here is h of x is this red polynomial, and it has 4 terms in it. I guess you can't see the x minus d at the end of that. But it's got four zeros, so it's 1/20th x minus a times x minus b times x minus c times x minus d, and that's off to the side in there. I guess you can scroll over and see it, x minus d. And so that's going to have 4 zeros here at a, at b, at c, and at d, and I can move those around and show you what it looks like. I put this minus 1 or 1/20th in there because if you have the graph as without that, it scales so large that x to the fourth is such a big number once you get outside of a close range close to 0 that the graph just looks like 4 vertical lines unless you zoom out, and it's just easier to scale it down and have make it smaller for our purposes. Okay, so you have a polynomial of degree 4 like this. And what we're going to talk about is called the multiplicity of the roots. So if you have 4 roots, what happens is x to the fourth is positive on both sides, and at every root it has to intersect the x-axis at that point. So kind of the only thing it can do is what this one is shown, down through A, up through B, down through C, and up through D. That's easy. But what happens if you have a multiple root? What happens if, pretend that A at B over here was equal to A? Then that's going to be x plus 4 squared, because I now have 2 roots that are both on x equals minus 4. So they give us 2 copies of x plus 4 in the factored form. So that's x plus 4 squared. And if you look at it, that looks like a parabola. That looks like x plus 4 squared if you zoom in on just that part of the graph. And so if you have a double root, if you have a squared term in your polynomial, it's going to come down and just touch the graph like a parabola and go back up. And if you look at it, what if they were not equal, but they are close by. Oops, that was too far. If they're close by, then the graph, oops, zoom out the other way, almost comes down and just touches, but it goes negative in between them. And as those 2 points get close together, that negative part kind of gets squeezed out, and then they're zero. That they're equal, and so it's a vertex of a parabola-like shape. And as B goes to the other side, oops, B goes to the other side, then A and B just flip-flop, and now B is farther to the left. So you can move these around. I could have A and C be the same, and so now I've got a parabola shape over here at 1, but it's upside down. So that's another double root, and for a double root, that would be, this is at x equals 1, so that would be like an x minus 1 squared term in my polynomial. And so that looks kind of like a parabola upside down in this case. And so you can look and see what a parabola or what a fourth degree polynomial is going to look like. It'll have an up and a down and an up and a down. Fourth degree polynomial will have 3 peaks and valleys, generally, but they could kind of hide. What if you had three points all together? So in this case, D, A, and C are all the same root. It doesn't anymore have 3 peaks and valleys because 3 of them have kind of combined into a single thing, and that looks like x cubed over here. If it's 3 roots together, that's going to be an x minus 1 cubed term, x minus 1 times x minus 1 times x minus 1. So close to that point, it looks like a cubed function. And then you've got another root over here on the left that brings it back up. And so what happens if we do fourth? As we get all 4 of them close together, then it kind of tiny wiggles between those points up and down on positive and negative, but generally it looks like it's a little flat at x to the 4th, and then a parabola-ish. It's not exactly a parabola shape, but it's up on both sides, positive on both sides. And so with this app, you can kind of play around with what these graphs would look like. So back looking at this idea of multiplicities in the book, what they talk about with identifying zeros and their multiplicities. So sometimes the graph will cross over the horizontal axis at an intercept, and other times the graph will touch and quote-unquote bounce off. So how do you look at that? Look at this function. You've got the roots are at x equals negative 3, x equals 2, and x equals negative 1. But the multiplicities, this one is x plus 3 to the 1 power, this one comes from the x minus 2 squared, and this one comes from the x plus 1 cubed. And so if you look over at x minus 3, it's a straight line. So it's like x plus 3 to the 1 power, and it's a straight line that goes through there, and it crosses over at that axis, at that intercept. At minus 1, it's this term x plus 1 cubed, and so it's going to look like a cubic function, like an x cubed function. And the last one is over here at, that's the x minus 2 squared. And so at that point, it's going to look like a parabola. It'll come down and go back up. And so you can draw a really nice rough graph based on just those little ideas. You know, and one other thing I should say is this one has, what's the end behavior of this? End behavior is, well, it's 1, 2, 3, 4, 5, 6. If you thought about this, this would actually be 6 factors put together. So it's going to be x plus 6 plus small terms. And so x to the 6th is an even power, so it's positive on both sides. So let's look at a different graph. Let's say this thing. Okay? We should be able to get a reasonable idea of what a function for this might look like. Well, where are the zeros? Where the zeros are here, here, and here. And what's the end behavior? The end behavior is odd. So it's x to some odd power. And I don't know exactly what it is. I have to count the multiplicities. But I can write down a function I'm going to have an x plus 5 term, and over here, this looks like a cubic. So I'll make it cubed. Okay, then I've got a term for this middle 0 at x plus 1, and this part looks like a parabola. So I'll make it squared. And what about over here? This last root is at x minus 3, so x equals 3 is where it's the root. And it could be a parabola, but it looks kind of flattened out, so I'm going to make it a 4th power. And so there could be other nuances in this. It's possible maybe this was a 6th power. We can't really eyeball it to see how flat it would be, but you can get a good sense of a typical graph that it could be here. And we've also got some stretching factor in here that I'm not going to worry about. Don't worry about in this case. Here. But this then is degree 9, right? The end behavior is x to the 9th. And so that all follows along. And if you graph this thing, if you graph it on your calculator, it's going to be enormous because 5 to the 9th is an enormous number. And so it's going to be really high up or really far down on your graph, and it'll probably just look like pretty much straight vertical lines unless you scale it well to make it look humped like it is in here. The last thing that they mention in this section is just a little way to remember. A way to write down the end behavior is this little notation. So let me scroll in for that. If you've got an even polynomial and it's got a positive coefficient, then it's going to be kind of like x to the 4th. X to the 4th or x squared or x to the 6th. And it's going to go positive on both sides. And so the way they write this is down here. As x goes to positive infinity, as you go off that way, the y value goes to positive infinity. So if you go off on the graph to the right, you're going to go positive. Here's an example below it. If it's a negative leading coefficient, like negative x to the 4th, as x goes to a positive infinity, y goes to negative. You go off to the right, you go down to the left. And here, if you go to the left, if x goes to negative infinity, your y value goes to negative infinity. So this is a way that you can write down the end behavior, but it's just a matter of do they go up and to the right or down when you go off to the right or left.